Welcome all of you in the lecture 22 of database. So today we will go a new topic in the indexing chapter. So that is basically the tree. So far in the data structure and algorithm courses you have learned about tree. Mostly you have learned about binary tree, which have two branches. So here we are learning a new type of tree, or the basic tree is B tree, from where the binary tree and other trees are comes. So the motivation is to have the dynamic indexing structures that can evolve when records are added and deleted, not the case of static indexes. So basically why we use the trees is for searching on the block devices. And another thing is both B tree and B plus tree are not the binary. So far we if we always think that a tree is always a binary tree, that should not be. So here we learn about B tree and B plus tree. These are not the binary trees. Objective is to increase the branching factor, because in the binary tree there are only two branch. Here we want to learn about the more branching factor about the trees. So the difference between the binary and higher order tree: binary trees designed for in-memory search, only the in-memory search. That is why the binary tree is created. Try to minimize the number of memory access. Whereas higher order trees, that is mean it having more branches than two. It is designed for searching data on the block devices. Try to minimize the number of devices accesses. So searching within a block is cheap, and this block type of memory using is increase the efficiency of the system of computer searching methodology. Now what is an MRE search tree? What is why we are saying that more than a MRE search tree, which is basically whenever it having more than two branches, it is called the MRE search tree. So the maximum branching factor is always m. Complete tree has the depth of log m base n. So if the branching factor are growing high, the complexity or the depth will be growing more, as log m base n. M is always the branching factor. Each internal node is a complete tree has m-1 key. So if you have a binary tree, if there is two branches, so each of the branch is containing one node or one keys. So here the number of keys is always m-1. So if there are m branches, if there are m segmentation, or if there are m pointers from a node, from a value, then the total containing keys will be m-1. Suppose binary tree is a B tree where m is 2. So as m is 2, so there are in the binary tree you have m-1, so that is 2 minus 1 keys for the each of the level. So B tree is a specialized MRE trees. So here each node has many keys. Subtrees between the two keys x and y contains the values v, such x is less than v is less than y. So that is basically, if you are looking here, suppose if we are saying here here the three here this is basically a seven branching factor tree. So there are 7 minus 1, there are 6 keys here. 6 keys can be here, so there are only 4 keys. So for these 4 keys there are 5 branches. So the first value, the first key is 3, so it is directed path is here, so the value of these node will be always less than 3 if it is the left side of this value, and the value of the right side of a specific node or a specific keys should be less than from the left one and from the right one. So the 3 is less than from x and is less than from 7, so x will be a value which is always greater than 3 and less than 7. So same by the same way in this node, this is comes from the 7, in between from the 7 and 12, so the value will be greater than 7 and less than 12, and the other is like that. And after 21 you see here that there is a right hand side, so this value is always greater than the 21, as it is have the left hand side the value is 21. So here for any B tree properties there are some specific value, that is the branching factor is always m. The root has between 2 and m children, or at most m minus 1 keys, so there should be a root. Whenever there is no value, so there is no root is needed, but whenever you have at least 2 node, there should be a root node. So all other nodes have between m by 2 ceiling and m records. So you see here the other nodes having the key value of m by 2, so m by 2, and this is the ceiling value and m records. And so if we look for a reality, the scenario is here, so there are 2 things here. One is the key and another thing is the data pointer. So if you have a key, then from the key to the leaf you have a left hand side and you have a right hand side. So left hand side is always the less than the key value, and right hand side is always the greater than from the key value. And if you have another value, it is here 16, so the value in the left side of 16 is should be less than 16 and greater than 7, and after 16 you see there, and there is another hand or another pointer here, so it is should be greater than 16. So here there is no keys, so as there is no keys, so the data pointer is null. As there is no keys, so that their data pointer is null, so there will be no pointer need to be created as there is no key or any data here. So if we look for a simple example here, you see here there are 2 key point here, 7 and 16 from the last slide. If you see there is 2 value is 7 and 16. So from here, if that is it is a tree, there are some leaf nodes. Leaf nodes are these ones. And right nodes are and these are the key nodes or root nodes. So in here you see that in the root node there are 2 values, 7 and 16. From the 7 there is a left hand side, so these values are 1, 2, 5 and 6 should be less than 7, and it is always less than 7. And from 1 to 5 and 6 there can be growing more level of data if it is necessary. And the second node is 9 and 12, whereas it is comes from here, so in between from 7 and 16, so these values on these node will be always greater than 7 and less than 16. Here you see there is another pointer starting after the right hand side of 16, so the value is greater than 16 always. So in this leaf, which values will become should be greater than 16. So if here there are no values more as in the previous slide. So as there are no values here or there, so there are the pointer are the null. So here you see that if there are no values here, that is no value here, so there are no more arrows here, so no more tree is created because the values are already null. So we can elaborate it here in more briefly that in this tree 7 and 16 is in the root node, so that's why in the left hand side the values are, the keys are always less than 7, that is basically. And in here the as the pointer is started between the 7 and 16, so the values is, the keys are always in the range of greater than 7 and less than 16, and the values are in this node is greater than 16 as it is the right hand side of this 16. So we come to a very basic tree. We want to create a very basic tree. How can we create? So suppose like assume a tree where each node can contain 3 pointers. So 3 pointers, what does that mean? So 3 pointer mean there are pointers, so there are the branching factors, right? So if you see there is a pointer, so these are the pointer, there's a 1 pointer, there's a 2 pointer, there's a 3 pointer, so these are the branching factor. How many branches are here? So there are 3 branches. Okay, so always remember the pointer is the branching factor. So branching factor is here 3, so enter the values 1 2 3 4 5 and 7. So how can we make it? So here branching factor m is equals to 3, so each node will contain m minus 1 equals to 2 keys maximum, and what the minimum value will be m minus 1 divided by 2 equals to 1. So that we already studied here that the maximum branching factor is m, and m, the root node can have the between the values or keys in between 2 to m children, whereas m minus 1 keys is the most value. M minus 1 is the most value, and the other, the less value can be m minus m by 2. So here we see that, so as our branching factor m equals to 3 here, so each node will contain m minus 2 equals to 2 keys is maximum, and minimum is m minus 1 divided by 2 equals to 1. So now if we want to insert the first value is 1. So as we say that our maximum keys can be contained as 2, so 2 will be the maximum value, so there should be 2 separated field or keys here that we can insert 2 datas at least, because the maximum value is 2. So we have to draw the trees, draw the node with the 2 space of maximum values, so that we can insert 2 datas in a leaf. So at first if we want to insert 1, so here we are inserting 1 in the, always starting from the left hand side. Then we want to insert 2. So now you see that in a leaf having 2 spaces, here we are inserting 1 already, that is blocked by a blue color, so another block is still free. So if you want to insert 2, the free space will be used, so we can insert 2 in the free space. So that is the thing. So 1 is already inserted in previous, and we are now inserting 2. So 2 is now occupied, and this is color is changed to the blue. So you need not to make your color blue whenever you are making the quiz or answering. It is, I am just making rational for your understanding. So inserting 3, whenever we want to inserting 3, so see that this node is already occupied because the maximum value it can have it is 2. So 1 and 2 is already here. So if we want to insert 3, so we need another node, right? So because here 2 value can be added, can be placed in a node, is that is the maximum. So if we want to insert another value, so we need another node. So in here there is only a single node, so it doesn't need any root node. Whenever you have 2 nodes, then you have to select a root node, because from a root node you can decide either you go left or right, so that you can find out the values of v. That is, we find in previous that v is less than x and v is always greater than x and less than y. So the root node is decided, you will, the next value will be go on the left side or the right side, because left side is directed the lower values and right side is directed the higher values. So what we is do basically split the node in the middle. So split the node in the middle, that is mean that there are 1, 2 and 3, there are 3 values here. So we will split here, we'll split here the node and make the middle one as a root, so that what we'll basically do is there are 3 values here, 1, 2 and 3. From there the middle one is 2, so we will split here and choose the middle one as a root value. So choose the root value, but please remember that as our branching as our maximum key values is 2, so all the leaves should be drawn in 2 spaces. So a root node is a space of 2, other leaf nodes are the space of 2. So we are making the root node is 2. So from 2, from the left hand side, that is 1 which is lesser than 2, and from 2 there is another branch or another pointer, so that is to the 3. So 3 is greater than 2, so the logic is compiled properly. Now if we want to insert 4, so what will be the thing? So if we want to insert 4, there are many spaces here. So as we want to insert 4, so what will be happen here? So 4 is greater than 2, so it will go in the right hand side of 2, and there is a 1 blank space just after the 3 because it is not occupied, so we can insert 4 here. So that is the thing. So 2 and 3 and 4 is here, so there is some space. When you want to insert 5, so you do again the same work, split and move up. So that was the tree for up to 4. Now you want to insert 5. So for inserting 5, there is no space in between 3 and 4 because it is already occupied. So where the value will be go? So if you split here 3 and 4, so what will happen? 3 having a space and 5 having a space, and 4 is going up. 4 is going up and 4 is seeing that here is any space or not. If here is some space, then it will goes here. If there is no space, then it will again following the rule of split and move up. So what is the thing is happening here basically? So 3 by this 3 and 4 it is splitting. So it is splitting, and 3, 4 and 5, the middle value is 4. So 4 is moving up. So 4 is moving up and it is going with the 2 in the root node. And if you see here, that is 2, from the 2 the left hand side is 1, which is the lesser by 2 and 4. So the value is 3. So 3 is greater than 2 and lesser than 4, and in the right hand side of 4, that is 5. So 5 is greater than 4. So the logic is totally compiled. So if you now inserting 6, so there is some space in here already. So 6 is greater than 4, so it will come to the right hand side of 4, and there is some space for 6. So 6 will be easily set on this parameter. So that is inserting the 6 here. So now we want to insert 7. So if we want to insert 7, again the same question is come. So split and move up. So if we want to split here the 5, 6 and 7, we will split here. So 6 will be gone up. So 6, whenever the 6 will be gone up, so there are two leaf here, creating two leaves. One is 2 and 4 and another one is the 6. So if there are two nodes here, so it needs a root again, because a root can only decide wherever you want to go, right or left. So if you have two nodes here in the root level, so these two are going to be a leaf node and it need another root again. So what is basically happening is you have to split the things. So the 5, 6 and 7, there is no space in between 5, 6 and 7, so you have to split it and split the full node, and you always split at the central value. Okay, so 5, 6 and 7, in between the three values, what is the central? 6 is the central value. Okay, so if you are always making is a sorting order, so you are finding the median value for the split, and then you promotion the middle value to the upper level. So that is 6, 5 and 7, creating this factorial whenever we are making the split and promote. Then the situation is come like that, as I said before. So 2 and 4 is in one node, so that is one structure, and 6 is upper level, and 5 and 7 is on the left and right side accordingly. So there are two root node, but that should not be, because root is always one node. So as the root is always one node, so we will take care of it here, 2, 4 and 6, and we make again the rules of split and promotion. So by this 2, 4 and 6, 4 is the median value, so it will be the split here and then move up to the forward level. So that is the tree. So here the tree, the root node will be the 4. From the 4 in the left side, that is 2, so 2 is less than 4, and from the right side it is 6, so 6 is greater than 4. From the here in the 2, in the left of 2 it is 1, which is lesser. From the right of 2 it is 3, which is greater than 2, sorry. And in 6 here, the left hand side it is 5, so it is lesser, and it is 7, which is greater than 6. So the tree is completed up to this point. So now we will practice some problem of the alphabetic order. So here are some values of S, W, A, E, C, T, M, L, P, Y, X, Q, B. So you will insert these values step by step. It is a practice problem. We will solve it in the next class, or you can submit to me in the group here. So that is the end of this lecture. Thank you all.